couple days ago, I was looking for my slippers. I opened the door to my closet, looked around, and didn't see it. But then I decided to look in the darkest of corners, and I found something that intrigued me. So I went over to my other room and examined it a little bit closer. Here it is all set up, and you might already know what this is just because of this coil here, but if we were to plug it in, this is a output of a 12-volt power supply. Boom! Plasma. I love plasma. So this is a Tesla coil that is driven by a Slayer exciter circuit. A Tesla coil is not it's a very simple device. It is just consists of a primary and secondary winding, as well as a straight capacitance between the tip of the secondary winding and ground. So in this case, the primary winding is just a turn of PCB trace that's going around the secondary, and the secondary is this big long tower of some super fine gauge magnet wire. Then it comes out of the tip. And on its own, the circuit would not oscillate, but because everything has a straight capacitance, there is just a couple picofarads between the output of this and ground. So that makes it oscillate at a very high frequency, probably around 30 kilohertz, and produces an arc. And the reason that I would not be getting shocked just by touching it is because this arc is at such a high frequency that nerves don't even respond to it. So it's essentially harmless to anything at lower powers, but at higher power, it will still heat up tissue. So, yeah. And that's why it burns, but doesn't shock. You might notice these two big aluminum uh, blocks. These are heat sinks for two transistors. Well, let's get that out of here. So this is the main transistor that switches everything. It's got a big heatsink because BJT transistors aren't very inefficient. You could use MOSFETs to increase the efficiency or cooling fan, but that would make it quite a bit more expensive. And this is a chip that would be required for the amplifier. But why would this need an amplifier? Well, it does not need an amplifier. But if you look on the side here, you notice the DC barrel jack, but also this mystery jack. Let's see what plugs in there. So what plugs into the mystery jack? An audio cable. This isn't like a headphone jack that it actually emits audio. This is an audio input, so you would have to use a male-to-male audio cable with two ends like this. But it comes with the kit anyway. So we would have to plug this in and plug the other end into a sound source. I mean, yeah, this is a very cheap portable cassette player, but it's all I have on hand for audio sources. So I'll just plug it into the headphone output. And beneath this row of heatsinks, there is a switch. And there are two positions. I know it's in Chinese, but I have figured out this is the position that you want it to be for standalone mode, and this is the position you want it to be for in audio mode. The audio mode is weaker, but it produces less noise. So let's flip the switch with my probe. Hit play on the cassette player, and then see if we can hear anything. Maybe move the cassette player a little bit away because because this thing produces a decent amount of interference. And let's plug it in. Do you hear anything? I hope you can hear something there. So what this does is it modulates the signal so that it can produce different frequencies, and those frequencies just happen to be the frequencies of some song that I'm playing. So it uses an arc to play back some sound. But this isn't a very good speaker. It's quieter than a headphone speaker, and it also produces a decent amount of interference. But how do I know this thing produces interference? Well, if I was to switch it back to the higher power mode, that doesn't take use of the audio jack, then turn it back on. There's our plasma, and turn it off so that you can see it a bit better. Well, it's a bit blurry, but there's the arc. Then we can bring close a small neon bulb, and look, it lights up. Why does it light up? Well, because this produces a strong enough electric field that there is an area around it where a low pressure gas tube like this small neon bulb uh, will be ionized and start to glow. And if you were to leave it here for a while, then it would get quite warm. So that's one example of how this thing produces interference. In fact, it doesn't have to be a neon bulb. Here's an LED, and if I hold this in a very specific position, it lights up. But if I turn it around, it turns off. That's cool, no? But anyway, now I want to show you how this thing interferes with radio signals. So here is a radio, and well, let's turn the Tesla coil off for a moment and turn the radio on. Oh, it doesn't have any batteries in it. Okay, so now the radio has batteries in it, and if I turn it on and set it to a decent station, but then I plug in the Tesla coil, yeah, you can see it produces a lot of interference. Yep. And in fact, this produces enough interference that the touch screen of a phone is pretty much completely disabled when it's on. I don't have another phone to describe it to you because I'm using the phone to film it on, but just please trust me once. So that is my review of the of a really of a Tesla coil kit driven by a Slayer exciter circuit. By the way, this thing was not assembled when it came. It was just a box of components, and it got some broken English manual to put it together, which I did actually need. And as you can see, all of the most of the stuff is in Chinese, except for just a few of the stuff. But yeah, most of it's in Chinese. uh, and I did cover this LED up with duct tape. It is necessary. It's not just like an indicator light. It actually is required for the Tesla coil to operate. If I were to disconnect that LED, then the Tesla coil wouldn't work. So I have to cover it with some dark material like duct tape to make the arc pop out a little bit more. So anyway, goodbye.